Hey guys, in this video I want to introduce you to a slightly different type of stoichiometry problem. To introduce this, I'm going to start by using a real-world example where these questions are relatively easy to figure out, even if you don't know how to do stoichiometry. All right, so we're just going to use the the example of just saying that you can take two wheels, combine it with one frame, and make a bicycle. All right, so it's just like a chemical equation. We have coefficients, we have a ratio between these things, and we could come up with some relationships. All right, we could say, all right, let's say you had a dozen wheels. All right, what's one thing that's always true about a dozen? It means 12. All right, if we had a dozen wheels, it would also have a weight. All right, so a dozen wheels would weigh about 36 pounds. All right, so that we could say that one dozen wheels is 36 pounds of, that should be. So a dozen wheels would correspond to about 36 pounds worth of wheels. All right, we could do the same thing with frames. All right, a dozen frames is 12 frames, and a dozen frames would weigh about 48 pounds. All right, so these two relationships are analogous to the mole relationships that we use in chemical equations, where we can say a mole of something is always just 6.02 times 10 to the 23rd, just like this one right here. And then we could say, if you had that many of something, how much would it weigh? All right, and that's analogous to this relationship right here. The glue relationship that we use in the chemical equations is just like this right here. So if we need two of these for every one of these, it's the same thing as saying if you had 2 dozen of this, you would need 1 dozen of that. All right, so the thing is, so far when we've done chemical equations, we've asked these types of questions here. All right, if you had 2 dozen frames, how many wheels would you need? All right, so the thing is, I think that most people could figure out the answer to this even without using stoichiometry, but hopefully you realize with this question right here, I could solve it with a crossbar. All right, I could start a crossbar with 2 dozen frames, and I could use these relationships here in the crossbar, setting up those diagonal relationships to end up answering the questions. All right. Another question, if you had 240 pounds worth of frames, how many pounds of wheels would you need? All right. And it's kind of weird to think that like we're, quantifying how many wheels we have by saying how much the total weight of the wheels are. But in chemistry, remember, we can't count out atoms. We can't count out molecules. We can only weigh them. All right. Actually, you can measure the volume, but weight is the most direct way of measuring the amount. All right, but when we're doing the reactions, we have to figure out the quantity, and that's why we have to do the use the relationships. All right, so the one thing I want to point out about these two questions right here is they are only, after we balance the equation, we're only dealing with things that are on the reactant side of the equation. All right, we haven't said, none of the questions here talk about anything on the product side. All right, but I think that we know that we could ask questions that would involve that. For example, I could say, if you have 10 wheels, how many bikes could you make? All right, or if you had 7 frames, how many bikes could you make? So those would be fairly easy questions because we understand the ratios between these. All right, but the thing is, there's a type of question that goes that's a little bit more complicated, but I think if you think about it, you can kind of understand how it would work. All right, and that question goes something like this: if we had 8 wheels and 5 frames. All right, so I'm giving you both a certain amount of one of the reactants and a certain amount of the other. How many bikes could we make? All right, so taking a look at this, and let's just kind of, if you want to jot it on a piece of paper, start matching up the wheels and the frames. All right, and I think what you're going to realize is that when we do that, we're going to use up all of our wheels, all right? And we're going to end up having one leftover frame, all right? So inevitably, unless you have the perfect ratio, one of your materials is going to run out first, all right? So when we start matching these up, I think you could figure out we would be able to make 4 bikes, and then we would just have a leftover frame, all right? So what this points to is this concept of a limiting reagent, all right? This is when you're matching things up in a ratio, the thing that would run out first is what's called the limiting reagent, all right? And the reason that they call it the limiting reagent is it limits the amount of the product that you could make, all right? So let me just give you a couple of examples here, all right? Let's pretend that we had 8 wheels and 5 frames. That's the one we just did, all right? Well, when we're doing this, I think most people could realize that your limiting reagent would be the wheels, all right? The wheels would be the thing that runs out first, and that we could make 4 bikes from that, all right? What if we had 8 wheels and 10 frames? All right, well, still, this one runs out first. That's your limiting reagent, and we can make a total of 4 bikes, right? Notice that the number of bikes that we could make had nothing to do with the thing that we had left over, all right? We have more than enough frames here, all right? The number of bikes that we could make are only controlled by the limiting reagent, all right? Let's give one more example or 2 more examples. All right, let's say that you had 8 wheels and 2 frames. Well, here's the situation's a little different. Your frames would actually run out and you would have leftover wheels. All right, so in this case, this would be your limiting reagent. All right, and you would be able to make 2 bikes. All right, what if we had 100 wheels and 2 frames? Well, still, you could only make 2 bikes. All right, because the amount of product that you could make is only dependent on the thing that runs out first. It doesn't matter how much extra of the other thing that you have. All right. Well, the thing is, the same concept applies when you're doing chemistry, right? So here's a chemical reaction. All right, we're going to take iron chloride. Actually, this would be iron 3 chloride. Combine it with zinc. We're going to make some zinc chloride and iron. All right, and I've gone ahead and balanced this, and I've also gone ahead and put the molar masses underneath each of the chemicals. All right, well, just like in the previous example where we said if you have a certain amount of one thing and a certain amount of the other reactant, how much of that product could you make? Well, what if we mixed 1.25 grams of this chemical with 1.10 grams of this chemical? How much of this chemical could we make? All right, and notice I stressed could, because that's different from saying will you make, because sometimes you don't, and usually you don't make that exact amount. And we can talk about the reasons for that a little bit later. All right, so just like before, we have to be able to figure out how much we could make. We got to figure out of the things that we're mixing together, what's the thing that runs out first? All right, so the problem is that to do this, we have to get quantities, like the number of things, like you could count. All right, it's not the total weight of the wheels that matter, it's how many wheels that matters. All right, because when you're looking at your balanced reaction, this isn't saying 2 pounds of wheels plus 1 pound of frames. It's saying 2 individual wheels and 1 individual frame. So these are quantities, right? So what we have to do in this problem here is we've got to turn grams, which is how much the total would weigh, into quantities, all right? And the way we do that is by turning them into moles, All right, so remember, moles are like dozen. All right, it's not the same thing as saying this is exactly how many there are, but if you said 2 dozen, you know that that's expressing quantity. All right, so let's set up 2 crossbars. All right, so to figure out the quantities, we're going to have to convert these into moles, right? Which is essentially a way of saying how many units of that chemical do we have. All right, so we're going to do what we've done before. We have a mass of this chemical, and we can convert it to moles by using the relationship that involves the atomic mass. All right, so we can figure out we have this much of FeCl3 and this many moles of zinc. All right, so you might think that the thing that runs out first is just automatically the thing that you have less of. All right, but let's take a look at something that's a little bit easier to figure out why we can't really do that. All right, so when you had 8 wheels and 5 frames, which do you have less of? All right, we actually have less of the frames, but which one runs out first? All right, it's actually the wheels. And the reason for that is we need twice as many wheels as frames to meet the ratio to make a bike. So the thing is, even though we could easily figure out which runs out first here, there's a little trick to figuring out what runs out first. All right, and that is to simply take your actual quantities and divide each of them by the coefficient in the balanced reaction. All right, so what are we dealing with? We need 2 wheels per 1 frame. All right, so what we're going to do here is we're going to divide the wheels by 2 because that's how many we need. I'm going to divide the frames by 1 because that's how many of those we need. And when you do that, this becomes 4 and this is 5. And what you want to do is compare these numbers. The numbers here, whichever one is less, would be mathematically the thing that you run out of. All right, so that's why this is the limiting reagent. All right, so we can do the same thing over here. All right, we know that, so this is how many units of FeCl3 we have. All right, so we're going to take that and we're going to divide it by 2 because that's how many of it that we need in the balanced equation. This one right here, we're going to divide by 3. All right, and we're going to use our calculator. So now that we've done that, we can see that this number right here is less than this number right here. So that proves that this is our limiting reagent. All right, so the thing about this is that you actually end up doing a lot of work up front just to figure out which one runs out first. All right, and the thing is, after you figure out that this runs out first, the amount of this doesn't matter. All right, so why does that not matter? Well, just think about these examples here. Once you figured out that the wheels ran out first, did the amount of the extra thing matter? Whether it was 5 frames or 10 frames, if this thing runs out first, you still got the same number of bikes. All right, so that's why after we figure out that this runs out first, we don't really need this number anymore. All right, to finish up the problem, what we're going to do is just start with this number right here. All right, so to finish up that question, we're going to start with this right here because that's essentially the quantity of your limiting reagent. All right, so we're going to start a crossbar with that right there. All right, then what we're going to say, well, okay, since that's the thing that runs out first, for every 2 of those things, we could make 3 of the thing that we're interested in. So where do these numbers right here come from? They come from the balanced reaction. All right, notice that's just a mole to mole ratio. And we can do a mole to mole ratio between any of these things. All right, and then once we get that into moles, we convert that to grams just by using the molar mass. And we calculate that we could make 1.58 grams of zinc chloride. Okay, so I understand that this is a little steppy at first, but it gets a lot easier with practice, and that's what we will do in class.